Okay, 13, you say. So it says you have this figure, and you're supposed to sketch a direction field over an appropriate grid. So let's make a grid first. So let's see, it looks like this is y. So y starts at -3 and ends at 1. So I will do this. 1, -3, -2, -1. I don't know about x. I'm just going to do this for x. Okay, so that's going to be my appropriate grid. And the reason why I chose that is because we have information about what this differential equation looks like between y equals -3 and y equals 1. Remember that this f here is literally the slope. It's the slope because dy over dx, slope, is equal to f of, well, f of y, I guess it is right here. And so for example, when y is -3, the slope is what, +3? Is that about what that is there? So that's +3. So the slope is going to be +3 down here. So let's just put a +3. And then when y is equal to -2, notice that the slope is -2. So that would be like this. In between somewhere, you have a slope of 0. So there's a slope of 0 somewhere closer to the -3. So what you have to do is imagine that this just tells you what the slope is going to be on our grid. So the slope when y is -3 is really big. The slope when y is -2.5 or 6, 2.7 is 0. And then when y is -2, the slope is -2. When y is -1, the slope is 0. So you see how this works out? So I'll put a 0 here. And in between, by the way, slopes are negative, but they're getting less negative. So like right here at -1.5, the slope is -1. So I've got to, okay, that's not quite -1, but whatever. You get, it's fine. Okay, then when y equals 0, the slope is 2. So at 0, y equals 0, we have a slope of 2, but somewhere in between, you have a slope of 1, so I'll just do that. And then at 1, the slope is really negative here. Wow, this is a terrible one, so I'm just going to do this. So here's how this is going to look. I'm going to draw, because this has nothing to do with x, f of y, there is no x in this differential equation. The slope will be the same regardless of what the value of x is. So once you have the slope at a particular y value, you can transfer it all the way across. These go like this. I guess these are all negative. They're good enough. So this is what we're looking at in terms of our slope field. Okay, whatever. Good enough. But this is sort of familiar, this idea of, you have these sort of flow, the flow is going to go across. This is autonomous, by the way. Yeah, so that's the sort of thing that you're, so it's similar to, where are the ones that we had that were similar? All the, oh, those are not similar. Did you have any you had to do? You had to make some, well, I guess we'll see how my quiz goes. Oh, these, did we do any of these? Okay, yeah, those autonomous ones. Yeah, so those, that's what this is. This is autonomous because it's a function of y. So similar to something like these, where are they? Like these. So here you have a function of y, so it doesn't matter what your x is, you're going to have the same. So you could just draw a phase line for like number 22, I would do. Y equals 0 is a equilibrium, and y equals 1 is an equilibrium. And then everything else, we just have to worry about which direction we're going. I guess we're going, let's see, when y is equal to 100, you're going to be going down. I should get rid of this arrow here and get rid of this arrow. When y is equal to -100, you're going to be going up. And then what happens in between there? when y is 1/2, you go up because the slope is positive. So that's this one. I don't know if that's one of the ones you had to do, but I'm just saying that this thing up here that we just did, this is similar to that because slope field will be the same left and right. All right, anything else from this that you have to do? All right, I've got a multiple choice thing. I guess it's not quite like anything that you had on your homework, but I'll bet you'll be fine. So why don't I pass this around? You can work on it while I do attendance, and then I'll collect it. There you go. There we are. Here, I'll just give you too many and make sure you pass them back. 1, 2, 3, 4. That's probably too few. Here, I'm going to give you too few because they have lots of them up front. There's some. Here, you can have all of those. Oh, here, you can have this. All right, let's see. Did we sort it out? You need an extra one? All right, let's see. He's got 2. Pass one of those back. Caden wants it. Yeah, reach. You want one? Well, I always do. I like to make sure that you have an abundance of quizzes. Okay. Let's get this up here. Okay. Either you can label these A, B, C, D, or draw lines. So I think I'll label them. The lines always look ugly, but you do whatever you want. So I'm going to label these like this. And then I'm going to put the letters next to the appropriate differential equation. Testing. Okay, this is working. Oh, sorry. All right, hopefully you're coming down the home stretch. You're just doing some matching here. Don't have to do too much, hopefully. Set up. All right, I'll grab homework first, and then I'll come back and grab quizzes. I need to get your folder set up so that I can just return them to the folder thing. Yeah, here we go. I know you want me to reach. It's good for me to do my stretching. Oh. All right, now hopefully I got all the homework. And so you can pass your quizzes over while I stack all this stuff up. And if you're still stewing over them, you could just start guessing at this point, I suppose. Very nice. Oh, nice. Some people did the line thing. Some people did the letter thing. I like it. All right, here we go. Good job. Nice work. I like it. Good job. Let's Excellent. What do you think? You're going to hold on to that? No, you don't want to hold on to it? Okay. Okay, I didn't know if you wanted to just hang on to it. Whoa. I like your lines and letters. Double up. Good job. You like it? All right. All right, do I have all of the quizzes? Staple. Done. Okay, let's see how we did. Okay, so here's what you're going to want to do with these. Dy over dx equals y squared. So what that means is that as you go up, so when y equals 0, you should have a horizontal line, and as you go up, the slope should get steeper. So that way, and as you go down, they also get steeper because y squared is always positive. So that's not it. Y squared. This looks good. Yeah, slopes are getting steeper as you get further away from y equals 0. So notice that at y equals 0, slopes are horizontal. Slopes are getting steeper as you get higher. So that is going to be number 1 is letter B. So in the same way, this negative y squared, slopes as you go up are going to get, negative. Negative for you. So here's horizontal at y equals 0. When y equals 1, you have a slope of -1. Y equals 2, slope is -4, and so on. So we want to see something like this, only instead of getting steeper upward, it's going to go downward, which is this one. Notice that here the slopes are 0, slopes are negative, and they get more negative as you go up, negative, more negative as you go down. So that's letter D. And then you can do something similar for these. Dy over dx equals x squared. You could actually solve this using calculus. The answer would be x cubed over 3 plus c. So x cubed over 3, that would match this one right here. Yeah, see, notice x cubed over 3 plus c. But anyway, also, when x equals 0, the slope is 0. When x is equal to 1, the slope goes up, and then it gets steeper. Okay, so that's going to be A, and this, by process of elimination, is what C is left. So hopefully we got it all right. B, D, A, C. Beautiful. All right, we're moving on. We're going to do this technique called separation of variables. So the first, you might have done this already. It's oftentimes, this is a technique that is covered in Calculus 1. So you might have seen this already, or sometimes in Calculus 2 as well, as an application of integration. So here is the general idea. The idea is that if you have a differential equation that looks like this, then you can separate the variables, hence the name, separation of variables, separate the variables and then deal with the variables independently, one at a time. I just want to show you what I mean by this. If you have something like this, dy over dt is equal to t squared times e to the negative y. Let's say we have something like this, just to show you what I mean by all of this. In this case, you have dy over dt, good, is equal to t squared. T squared is taking the place of the f of t. So t squared is f of t. And then g of y is the e to the negative y. So this thing is g of y. Okay, so what this says is that you're going to rewrite that by doing some algebra, but it's not really algebra. I know it looks like algebra. So if you want to think of it as algebra, that's fine. What it is you're employing some calculus, specifically the chain rule that says that you can rearrange the differentials in a very special way, but it ends up looking like algebra, and that's totally fine to think of it like algebra. And so the algebra is that you divide both sides by e to the negative y. So I have dy over e to the negative y. And then you multiply both sides by dt. But once again, what's really happening is that we're using the chain rule to separate the dy and the dt, but let's not be picky about this because it looks like this, and that's totally fine. Next, you're going to integrate both sides. Before I integrate the left side, though, I'm going to just do a quick rearrange. E to the y dy is equal to t squared dt. So you see I've just gotten rid of that negative exponent. And then we're going to integrate. And now that I've got the variables separated, I can pretty easily come up with the antiderivatives. I think you can all do this. Claire, what's the antiderivative of e to the y? Very nice, e to the y plus c. So e to the y plus c. All right, Matthew, what about the integral or the antiderivative of t squared? All right, t cubed over 3 plus c. Now, here's the thing about this, is that there is a constant of integration for this side, and there is another constant of integration for this side. And if you just move this constant over here, like you could call this constant 1 and constant 2, and combine them, they'll form a single constant. You only need one constant is what I'm getting at when you're doing integration like this. So you can leave it off of the left side and just put it on the right, or vice versa. I don't care which way you go. And that's sufficient, just like this. Now, if you are really obsessed with doing this, you could solve for y. That's not too bad in this case. Whoa, what just happened? Oh, it just all disappeared for some reason. Okay, let me rewrite it. Sorry about that. E to the y is equal to, what was it, t cubed over 3 plus c? Yeah, okay. Anyway, so if you're really obsessed, let's see if I can do this without, there, erased because PowerPoint, I don't know. Is you could write this like this, that y is the natural log of t cubed over 3 plus c. So then you have an explicit function or an explicit solution. That's what that is. That's an explicit solution. This, before I solved for y, is implicit, an implicit solution. Sometimes that's the best you can do. Sometimes you can't get a nice explicit solution. But this is ideal because we want to have a function so that we can predict the future. Like if this is supposed to govern some sort of like the temperature over the next 2 days, let's predict the temperature next week or whatever it is. Okay, so let's try this. It's really not too hard. Let's do this one here. See how you do. So take each one of these. We'll do one at a time though. And we're going to find the general solution. By general solution, I mean it's got a C in it. We'll talk about what happens when we have a particular solution in a minute. But go ahead and try these. See how you do. And then we'll work together. You can work with a friend if you need to. In fact, doing it with a group, of course, on your homework is always the best. So if you don't have a homework group, you should find a homework group. There, nice and big. Excuse me. Well, let's do some separating, right? Separate or equal or separation of y and t. I don't know. So let's go ahead and, Zechariah, what do you think of this first one? Can you separate those variables for me? Oh, okay, I like it. 2y to the negative third dy. All right, very nice. Now, just so you know, if you did this different from what Zechariah did, it's fine. The main thing that you want is you want all the y's on one side, and it might be dy over y cubed. It's probably the typical thing. And then maybe you'd simplify it to be this. And you want t dt on the other side. And the 2 can go wherever it wants. You want it to be on the right, great. You keep it over there. If you want to move it over like Zechariah did, that's fine too. Whatever you want. It doesn't bother me. So either way goes, it's fine. Okay, so next step is to do some antiderivatives. Let's stick with the way Zechariah has it. I think that there's some benefits to having that 2 over there. But go ahead and do those antiderivatives, and then we'll see how you did. And let's just agree for now that whenever we do this, we're going to put our constant of integration on the right side, not on the left side. So whatever we get, let's just put the c on the right side just for consistency. Tyler, what did you get for the left side of this thing? What's the antiderivative? All right, very nice. So negative y to the negative 2. So here's where maybe this is beneficial to put the 2 over there. So when you do the antiderivative, you divide by 2, and then that ends up canceling. So remember your power rule for integrals. And then, Adric, what about the right side? What do you get? All right, beautiful. T squared divided by 2. Now, at this stage, this would be considered a perfectly fine implicit solution. So implicitly, this is correct. But if you want a single function, or in this case, we're going to get 2 functions, we're going to want to solve for y. And most of the time, it's not going to be a terrible process. So let me just go ahead and do that. I have y to the negative 2 is equal to negative t squared over 2 minus c. And it's going to feel really weird to you, perhaps, to do what I'm about to do, but we're going to do it anyway. Anyway, y to the negative 2 is the same as 1 over y squared. And so I'm going to reciprocate that. So y squared is equal to 1 over negative t squared over 2 minus c. And then y is equal to plus or minus the square root of 1 over negative t squared over 2 plus c. Oh, sorry. I was thinking one thing and I wrote another. So, but I'm going to write what I just did. I'll explain what I just did. The thing about constants is that they are constants. And we don't care what we call them, like the name, like for example, let's say that my constant, I'm going to call it Frank. Frank is my constant, and Frank happens to equal 2. Well, someone else might call the constant George and might say that that constant is negative 2. Well, in this case, Frank and George are basically the same constant, just one is the negative of the other. In the same way, over here, I could have this constant. You've called this constant c. Maybe someone else called it constant c1, and it turns out that c1 is the negative of c. Whatever. In which case, that other person might write this. 1 over negative t squared over 2 plus c1. There may be good logical reasons for doing this, but I'm only doing this to point out that I can rename my constant as much as I want, as long as I keep it constant. So here, negative c, so whatever c was, let's just rename it. C1 is the negative of whatever c was. And then I can write this. That way, I can be more comfortable, which perhaps you don't suffer from the same thing that I do, but I am uncomfortable having a negative under the radical. So this allows me to write this. And notice that this feels a lot less negative than that did. Maybe it didn't bother you, but it kind of bothered me. So you can rewrite constants as much as you want and manipulate them. So sometimes, I guess I also mentioned this because sometimes you'll go to the back of the book, you'll see this, and you'll say, you'll lose your mind. Oh, I got it wrong. No, you didn't. You have this, the back of the book has this. They've just done some algebraic manipulation. More likely than not, that's all that's happened. So rather than trying to start again, focus on the constant, and if you can't figure it out, come ask or send me an email, and I will do my best to explain. Maybe you do have it wrong, but probably not. Okay, so there's that one. Let's do the second one. So I'll give you a minute in case you haven't done it already. I mean, hopefully you did it, but in case you need to finish. Sorry. Oh. There we go. Well, Cooper C, did you separate those variables? Okay, let me do this for you. Let's see. So you want to put t dt on the right side, and then on the left side, what are you going to divide by y? All right, good. And then what happens to this t squared plus 4 that's hanging out front here? Okay, so I'll divide it on the right side. Yeah, so it may take a couple of steps like this to get everything looking good, but here's t over t squared plus 4. How's this? dt. That's not bad. In fact, I think probably I'm going to do this without rewriting just because it'll be easier. 1 over y dy, if that's okay. So there's the separation of variables. We've got the t's on the right, the y's on the left. Now we can be happy. So we're going to do antiderivatives now. And as before, I'm going to put my plus c on the right-hand side. Rachel P, what is the antiderivative of 1 over y? Do you know? It is, very good, natural log of y. All right, now everyone's excited about this next one, right? All right, so Rachel J, what do you think of this right-hand side? Can you do it, or do you need to do a stepping stone? Wait, where's Rachel J? She skipped, there you are. Sorry, you were hiding behind Luke. No, it's not parts, it's the other technique. What was that one called? It was, yeah, that thing with the U's, right? Yeah, U substitution, very good. So we'll do U substitution with this. I'm going to do it pretty quickly, just because you've probably had this beaten to your head at some point. So I'll just crank it out right here. I'll go like this, and then eventually I'll get back to this. Okay, so U is equal to t squared plus 4, which means that du is equal to 2t dt, which means that we're looking at this. 1 over t squared plus 4 times 2t dt, but that 2 can't just magically appear. It has to balance with something, so I put a 1/2 out front to balance it. By the way, just because you have a 2 there, just be cautious. I've noticed in Calc 2 that some students are just thinking that they're going to magically put a 1/2 every time they do integration by substitution. I don't know why. Well, I guess because it's pretty common. Anyway, now I've got 1/2 times the integral of 1 over u du, because this is my du, this is my u over here. And we all know, actually, we already did this, natural log of y. So this is going to be 1/2 natural log of the absolute value of u plus c. So that becomes this, 1/2 natural log of t squared plus 4 plus the constant. All right, if you got this, you're doing great. You're doing great. Good job. We can do better though. We're going to solve this for y. So bear with me, a little bit of algebra and some fancy exponential and logarithmic combinations. So first things first, I'm going to deal with the logarithms, and specifically I will raise e to the power of each of these sides. So it's sort of like this. I'm going to rewrite this so that you can see what I've done. Well, maybe I don't need to. Do you see how I've taken each of those and turned them into an exponential? Because the opposite of a logarithm is an exponential, right? I want to get rid of the logarithm, so e to the ln of y is going to just equal y. Well, not exactly. It's going to equal the absolute value of y. We'll deal with that in a minute. The rest of this stuff I have on the right-hand side. This is going to require a lot of extra work. I have e to the natural log of the square root of t squared plus 4. And the reason why it's the square root of t squared plus 4 is because rules of logarithms say that if you have an exponent, or no, if you have a coefficient in front of a logarithm, that coefficient can move inside and become an exponent, and this to the 1/4 power, or the 1/2 power, is the square root. Let's leave that plus c there for just a minute. So that was a rule of logarithms. By the way, you're going to be using these rules. Maybe I should jot them down. I'll put them down as we use them. How about, let's see, can I get a different color? Where's my colors? I don't know. Okay, I'll just do this. Sorry, this thing did something weird. Okay, that's better. Okay, so the rules of logarithms. The one that I just did was this. If you have a times the ln of x, it's the same as ln of x to the a. So I'll just put this in a little bubble, 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 bubble. So just a reminder, that's what we just did here to here. Now the next little trick I'm going to use is this. If you have e to the a plus b is the same as e to the, e to the a times e to the b. So this is a rule of exponents, and you can kind of see where I'm going to use that. Specifically, it's going to be right here. E to the ln of the square root of t squared plus 4 times e to the c. And then the third rule that I'm using, at least in this problem, is one that we've already used, and that is if you have e to the natural log of x, those are inverse functions, you just get x. So e to the natural log of absolute value of y is absolute value of y, and e to the natural log of the square root of t squared plus 4 is the square root of t squared plus 4. We're getting close. I'm going to rearrange one more time, and then I'm going to rename my constant. So my rearrangement is this. Y is either the positive or the negative of the right-hand side. So the absolute value can turn into a plus or minus on the other side of the equal sign. And I'm going to move the e to the c up front so that we can write this like this. Now for my my renaming of the constant. So let's say that your constant, you decide to name the constant this. This is a constant. Either your positive e to the c or your negative e to the c. Whatever your constant is, it's this. I'm just going to rename it. And I'm going to say that I want let c1 equal whatever you got for your constant. So whatever your constant is, I'm going to get basically the same thing. It's just mine is going to look prettier. So these are the same because this whole thing is a constant, and this is just renaming that constant. There it is. So there's my general solution. Beautiful, isn't it? So, all right, now we have to deal with particular solutions. But before we do that, I want to make sure that no one's completely lost or somewhere. That's a lot. That's a lot of stuff. It's a lot. Take your time. Try not to make it too tedious. Okay, let's deal with particular solutions, then we can go home. Okay, particular solutions. Where is an example of a particular solution? Here is one. So I want to solve this initial value problem. Notice that I have a differential equation and I have an initial value. So take a minute and start with the differential equation. That is separable, so you should be able to separate variables. So go ahead and separate the variables, and then we'll go from there. Let's see where you are in terms of the differential equation. Oh, it's useless. Oh boy. All right, let's see how we're doing. Finish this up, and then we can get out of here. Luke, tell me about this differential equation. How am I going to separate these variables? Perfect. So you can put the negative on either side. If you want to put it on the left, great. If you want to put it on the right, that's fine too. Either one, I don't care. All right, excellent. Now we can do our antiderivatives. Nice, easy antiderivatives here. Madison, what's the antiderivative of y with respect to y? Very nice. So y squared over 2. And since Madison did that for us, I might as well just use the same thing, her work. I know it's cheating, but it's the same as the right-hand side, except for there's a negative there. And then we can put the plus c. Just always put the plus c on the right, just for consistency. All right, now we can maybe multiply everything by 2. Let's do that. So y squared is negative x squared plus 2c. I know what you're going to do is you're probably going to want me to just replace the 2c with c1. But before we do that, let me just point out that y is equal to plus or minus the square root of negative x squared plus, we'll call this c1. We're going to let c1 equal 2c. This is optional, by the way. What I just did here with the C1 and 2C, you don't have to do that. You'll get the same final answer as me, whether you do this or not. This is just to make things easier. But if you don't think it's easier, don't do it. Do your, keep the 2 there. It's whatever. Okay, now let's go ahead and figure out what the particular solution is. So I need to figure out which of those, whoops, I don't know where to go. There it is. Which value of C1 makes this true? Now, let me just point something out about this, is that this is negative. So you see that negative there in front of the 3, negative 3? Because of that, I know for sure that this is going to be the negative square root of negative x squared plus C1. So that's the first thing to note, is that because of the negative, this will be the negative, not the positive, it's the negative branch. This happens quite frequently in differential equations is you'll have something like this where there's a plus or minus, and you have to figure out is it the plus or is it the minus. Usually it's pretty easy to figure out which one you're going to use. But your final solution should not have plus minus in it. It should either be plus or minus. Okay, so we've got that -3. So we're going to say -3 is equal to the negative of the square root of -4 squared plus C1. So I'll give you a minute. See if you can solve that for C1. I'll bet you can. It's not hard. Andrew, what did you get for C1? 25. Very good. Now, if you weren't as quick as Andrew, let me just point out what you would probably do is, first of all, get rid of all those negatives. So much negativity. We don't like a lot of negativity, do we? And then square both sides so that you get 9 is equal to -16 plus C1, and then add 16 to both sides. So 25 is C1. And that gives us our final solution to this initial value problem. It's the negative of the square root of 25 minus x squared. So I just rewrote that because I don't like having the negative in the front on this. So I put the C1 out front, if that's okay. Now, just to show you, to remind you where this is coming from, if we were to draw the various solutions to this differential equation, these are the family of solutions to this differential equation for different values of C, look like this. They're all like half circles. They're all half circles, sorry. So it's either the bottom half or the top half. Same thing goes this yellow one, even though they're both yellow, it's either the top or bottom half, plus or minus. Same thing with the pink one. So that's what all the solutions look like this. And once you've identified an initial condition, you know that you're on this particular solution. So the general solution is just all of them. And then the particular solution is the one that you're interested in. So we've had pictures like this before, but now you can see how we're actually using them with an actual differential equation. All right, let me just see if this next one is at all interesting. Well, oh, I should mention this. Yeah, the next one's not that. The next one's just annoying, let's just say. It's got trig functions. Who wants to deal with that at this hour of the day? Let's just do this. Is just to mention that if you have an autonomous differential equation, autonomous differential equations are all separable, meaning that there is no t, and so you can always solve this, or at least do the antiderivative. You can always separate. Just put the t on the right-hand side, leave it as just 1 times t. And so you would do something like this. I'm not going to solve this one, but you can see that this is relatively easy to solve. So you'd have dy is equal to 1 dt. So my solution is going to have a t over here and whatever over there. What is it? Y squared plus 3y. So that's going to cause some problems, but whatever. Another thing that we should mention is that sometimes you're going to find that there are solutions that are missing from if you solve this using separable differential equations. I'll do this one pretty quickly, but I want to mention before I get started that one solution to this differential equation is the one that I forget someone had mentioned early on in this course, and that is y equals 0. Y equals 0 is a solution, isn't it? Look at it. It's obvious. Like when y equals 0, the derivative is also 0. So y equals 0 is a solution. But if we solve this using our separable techniques, check it out. We get dy over y squared is equal to dt. We're going to integrate both sides, and that gives me -1 over y is equal to t plus c. Sorry. And so that means that y is equal to 1 over c minus t, c1 we'll call it, where c1 is the negative of the positive c. That's not so important. I mean, you could do this yourselves if you were more careful, if you went slower than me. But what I wanted to point out is that none of these, none of them are y equals 0. And so every now and then you're going to have a solution that does not appear in your general solution. So the general solution doesn't include the one obvious one that at least someone came up with early on. So that sort of thing happens with separable differential equations. And then one last thing, although I've already mentioned this a couple of times, and that is that there are going to be times where the differential equation results in something that is too hard to solve explicitly. This is an example of such a differential equation. I'll just, without going through the gory details, let me just point out this, that the general solution to this is this. Give me a sec. T squared over 2. You could do this yourselves. It's not that hard. So separate the variables and then you solve, but you get natural log of y plus y is equal to t squared over 2 plus c. I cannot solve this for y. And so because of that, this is as good as it gets. You have an implicit solution. So if we can solve for y, great. But if we can't, doing the best we can. There you go. All right, hopefully you can do the homework. It's not all that hard, but feel free to hit me up. I've already got people making appointments. So I just got a notification that someone made an appointment for tomorrow. So feel free to do so as well. And we'll see you on Wednesday if you don't want to come see me tomorrow. Oh, coffee hour tomorrow. Reminder, every Tuesday now. It's only on Tuesdays at 2:30, is it?